Let's start by making a part I called it triangular. It's 2D planar, deformable shell, approximate size of about 1. So here I've made an equilateral triangle, dimension of 1 meter on a side. Well, let's set the property. I'm going to create one. I'll call this rubber. And we're going to need density, and we're going to need elastic properties. So for density, let's say a mass density 1,000 kilograms per cubic meter. And then for these elastic properties, I'm going to say a modulus of 1 million, Poisson ratio of 0.3, let's say. The section, we'll call it, I call the triangle sections homogeneous solid. And the material we're going to use is rubber, plane thickness of just a unit of 1. And then we'll assign this to the triangular element. Then under assembly, we'll create an instance. Since this is a dynamic analysis, we're going to need a few different steps. So we're going to go to Step Manager. The initial step, what we're going to do is anchor the lower left and the lower right corners of our triangle. Then we're going to create a new step. We're going to insert this after the initial one. And I'm going to call this one Pull Tip. So we're going to pull the tip of the triangle to the right a certain distance. So we're going to apply a boundary condition on that step. And we'll accept the defaults. And now what we're going to do is create a new one. We'll call this Release. We're going to release the tip at that point. We're going to use this as going to be a dynamic implicit. So what we're going to simulate is we're going to pull the tip of our triangle to the right, and then we're going to release it, and we're going to look for an elastic response. So here, instead of accepting the defaults, what we're going to do is we could set a time period. You could set this to whatever you want. If you wanted to animate this over 100 seconds, you could do that. It's going to take longer to analyze it. Let's just stick with the time period of 1 second. And then incrementation, this is going to, we're going to calculate the position of this triangle as a function of time. So the maximum number of increments, well, the first thing I'm going to do is I'm going to say this is fixed. So that way we can set the increment size whatever we want. So the maximum number of increments, this doesn't matter so much, but it'll terminate the simulation if it exceeds 10,000 increments. So if you don't want it to go too long. The increment size, this will be in seconds. And let's set this to 5 milliseconds. So there's going to be a total of 200 increments because we're updating it every 0.005 seconds, and we're going to let it run for a total of 1 second. So we'll see how many times that triangle goes back and forth over 1 second. So we'll accept that. So now we've got our different procedures. Initially, we're going to set the corners. We're going to pull the tip in the second step. In the third step, we're going to release it and then analyze the motion. So under Load, let's go to Boundary Condition Manager, and what we'll see at the top is there's going to be an initial step, the pull tip step, and the release tip step. So let's create a boundary condition, and we're going to apply this on the initial step. We'll just call this Anchor Corners, and it's going to be a displacement. We'll continue on that. So let's set the lower left corner and the lower right corner. And what we're going to do is prevent rotation in the number 1 and number 2 directions. The next thing we're going to do is we're going to create a new one, and we're going to apply this under the pull tip. So this is going to be a mechanical, a displacement, and now we're going to select this upper node, or that upper corner of the triangle there, and what we're going to do is displace that upper corner a distance of 0.2 meters to the right. And in our Boundary Condition Manager, let's rename that one. We're going to rename that. We'll just call this Pull Tip to the right, and that's going to be our boundary condition there. So now we can look at this thing, and the first boundary condition, we're anchoring the corners at the initial step. We're going to propagate that through to the other 3 steps. So in Pull Tip step, the corners will still be anchored, and then releasing it, it will be anchored. The pull tip to the right won't occur at the initial step. It will occur at the pull tip step. So let's take a look at this. So the pull tip, we've created the one, and then in the release tip step, what we're going to do is click here and deactivate that boundary condition. So that will effectively release it once we hit this step in the simulation. So let's dismiss that. One thing I want to mention here, if we go back to Step Manager, and this pull tip, let's edit that again. We're going to go back. In this pull tip, let's apply that not at 1 second. This is actually kind of arbitrary. Let's just apply it at oh, I don't know what, a tenth of a second after it quote unquote starts at the initial step. So our time, this will occur at 0.1 seconds. So if you envision a tenth of a second goes by before we shift the triangle to the right, but it's not going to affect our dynamic analysis, whatever we put there. So now let's go back, we'll go to the mesh module. What we're going to do, let's just make this one gigantic element. We're going to seed the edges. Let's seed all three of these, and we're going to go by number. We're going to set this to 1 just so we can create one element. And then we're going to go to mesh controls, and we're going to call these triangular elements. We'll say OK there, and now we're going to confirm. So the geometric order, these are going to be linear triangular elements. So it's a CPS3. It's a 3-node linear plane triangle. And then we're going to create the mesh. So we'll mesh the part, and we confirm there is just one element in our part. So we're going to query the mesh, and what we see, there's 3 different nodes at each of the corners, one element. We're good there. So we've created the mesh. So let's go ahead and create a job. We'll just leave the default job 1. So let's submit this job, and after we submit it, let's click monitor so we can keep an eye on it. So we've started it. It says step 1. And now step 2 is going. Remember, there's 200 different increments, so this comes down. What this tells us is the time for each of the steps. Now this is 0.1 seconds. We started step 1, for example. The total time, the next increment, we incremented this 5 milliseconds at a time. So this gives us the total time. To the right here is the time that is occurred for within each step. So within each step, step 2, for example, we're incrementing at 5 milliseconds, and as we scroll down, we've completed 200 different increments. So we can dismiss this, and let's go to results. And now within results, let's click this button, Animate Time History. So when I click that, what we can see now is the triangular element oscillating back and forth, and we're careful to look at this step time is in units of seconds again, based on our units. So this will animate up until we end it at 1 second. And notice that we can click here for the frame selector, and we can kind of go back and forth, and with each frame we are oscillating 5/100ths of a second, 5 milliseconds for each of these things, so we can see the thing animate. If we want to, we can go back to step, and we can edit within the step manager. We can edit this dynamic one, the release tip. So we'll edit that, and instead of an incrementation of 0.005, let's try 0.001. So we're going to get a little bit more resolution on our animation. So I'll go back to job and submit the job, go to monitor, and what we see, these increments are going up over time. Remember, the total time is going to end at 1.1 seconds because that first step had a duration of 0.1 seconds. So this column here, the simulation ends right now when that step reaches 1 second. We're completed. Dismiss that. Let's go to results. Sometimes this dialog box appears. I don't think it means much, but just in case, what I'll do is right-click here and close it, double-click here and reopen that job. I don't know if it makes a difference or not. But then I click animate on it. Now we've got a higher resolution for each of the steps. We see that the step is incrementing 0.001 seconds, 1 millisecond at a time. And if we want to, we could see things like when we animate this, we can see the stress occurring. What we could do is look at stress 1,1, and there is no stress in the x direction. In S22, we're not stretching it in the vertical, but what we do see is the shear stress, S12, does vary over time. Now it's a positive stress. We're coming back to the left. It goes back negative again, so it changes color over time. Let's go back to the mesh. One thing we can do is let's assign a different element types. Instead of a linear triangular, we're going to set that to quadratic. And what that does is it assigns nodes not only at the 3 corners, but it also assigns them at the midpoint on each side. So if we go back to the job, after the job is finished, we'll go back to the results. And now when I click animate, the element is able to deform at each of the intermediate nodes. You could also run this with a finer mesh and see what it looks like. Alright, let's animate this thing. Yeah, this is interesting. We can see the stress kind of propagating throughout the triangle. If we look at this, let's just look at the shear stress S12. and animate that. So here, if we go to ODB display options, we could average the elements at the nodes. And what this will give you is something a little bit artificial. Let's pause it for a second. Each one of these, this particular element, stress throughout one of these elements has to be uniform. And what this is doing is averaging the stresses across each of the 3 nodes associated with each element. So this is a little bit of interpolation. It's not very realistic, so I always turn that off. So we turn off the averaging at each one of those, we come back, and this is more realistic. The stress according to these types of elements is going to be uniform across it. So I'm going to go back, set the elements back to quadratic triangular. We'll take a look at what that looks like. So now we're back with the quadratic elements, also known as linear strain elements. I had to coarsen up the mesh a little bit just to stay under our 1,000 node limit for the student version of it. So now animating this one, what you can see are the little, within each element, you can see the deflection within the midpoint of each of the edges of the nodes. So I'll just let this play out so we can watch it.